Let's talk a little bit about limiting reactants. So with limiting reactants, what we're dealing with are stoichiometry, where we have to ask a really simple question, and that is, do all reactions actually go to the completion? And the answer there is, well, yes, of course they do, but that doesn't necessarily mean that everything that was a reactant turns into a product. So let's take a look at a simple example. Let's say that we are burning charcoal. Carbon in the presence of oxygen makes carbon dioxide. So that's basically what happens when charcoal burns. Now, if we were, say, to ignite a brick of charcoal in a big open room, it would be pretty safe to assume that all of the charcoal would burn, right? It'd be very unlikely that it wouldn't. But we also understand that if we took that same brick of charcoal that was on fire, put it in a jar and closed up the jar, charcoal probably would eventually snuff out. The fire would stop and there'd be a bunch of unreacted charcoal left over. So what gives there? Why is it that we can have a reaction going 1 minute and not the next? Well, what it comes down to is our understanding of limiting reactants. So we need to look at some terminology here. First of all, what is a limiting reactant? Well, a limiting reactant is the substance, the reactant, that ultimately limits the amount of product that you can make in a chemical reaction. So in the case of that charcoal example, when we lit the charcoal inside of the big room, well, the charcoal didn't run out, but chances are pretty good there was oxygen still in the room after we did the reaction. And if it didn't, then we would have problems of our own for being in the room that was lit with the lit charcoal, because we need oxygen to survive also. So limiting reactants do have an impact in that kind of way. So every reaction that we can think of has a limiting reactant, something that is going to run out first. And once we run out of that substance, the reaction as we know it stops. When that happens, there's usually an excess reactant, something that we had more than enough of. And as a result of having more than enough of it, there's left over when the reaction is done. That's what makes it excess. Now, it is possible that you can have both substances in a chemical reaction be limiting reactants. If we do a reaction and we measure out everything very, very precisely, and we do the reaction and all of the reactants react and there's nothing left over, what that is called is a stoichiometric amount. That's basically the exact amount that we need to do the chemical reaction. Now, the only way that we can get stoichiometric amounts is by measurement. And that usually involves calculations of stoichiometry, which is why it's called a stoichiometric amount. But I want you to think about this another way, possibly. Maybe something that's a little bit more familiar. Let's say that for the sake of argument, that we have a hamburger store, and I'm going to pick on Wendy's here because Wendy's was my first job in college, and they have a soft spot in my heart, not because I was the best worker or that they treated me, particularly well. They treated me like any other job did, but mainly because it was my first. Now, let's say that the whole idea of customization is out the window, and this is how you make a cheeseburger. Cheeseburger has a bun, it has a hamburger patty, it has a slice of cheese, it has pickles, it has onions. That's what we're going to make today. That's what we're doing when we sell cheeseburgers. Well, each of these substances, the bun, the patty, the cheese, the pickles, and the onions, we can think of as reactants in this rather complex equation to make a cheeseburger sandwich. The question I would have for you then is this. If Wendy's has all of these ingredients in tow, and the recipe is as follows: how many cheeseburgers could we ultimately make? So if I only have 13 buns, if I have 5 pounds of hamburger meat, if I have 25 slices of cheese, if I have 100 pickles, if I have 30 onions, how many cheeseburgers would that make ultimately? So take a second and just sketch it out somewhere. Try to figure out what it is that you're going to do, how many cheeseburgers you can ultimately make. And I will reveal the answer here in 5, 4, 3, 2, 1. So the answer here is actually relatively simple. We can just take those ingredients, figure out how many burgers we can make with each of them, and then we know that whichever one runs out first, well, that's when it stops. So the 13 buns, well, we know we can make 13 burgers out of that. Since each burger has a quarter pound of meat, that means I can get 4 burgers out of every pound of meat. I can make 20 burgers with all the meat. With the 25 slices of cheese, I can make 25 burgers. With the pickles, I can make 50. With the onions, I can make 10. So when all is said and done, the end result is I can make a whole 10 burgers with all of the cheeseburger material that I had previously. And that's an important thing to know, because under our definition of what a cheeseburger is, I can only make 10. Now, anyone could look at this and say, okay, well, hold on a second. You're going to have a few buns left. You're going to have some meat left. You're going to have some cheese and pickles left. Couldn't you make cheeseburgers with those remaining ingredients? And the answer is yes, to a degree, but they wouldn't be the kinds of burgers that were specified in the recipe. And the same thing exists in chemistry as well. With the excess reactants, could you make more stuff? The answer, of course, is yes. Yes, you could, but it would not be the same stuff that the original chemical reaction was intended to make. And so under this example, onions are going to be the limiting reactant because they're going to be the thing that we run out of. Everything else is going to be in excess. Now, something else that we can look into and that we can look for is, well, if I make those 10 burgers, how much of the other stuff is left over? Well, I can see that there will be 3 buns. I can see that there will be 10 burgers worth of meat. I can see that there will be 15 burgers worth of cheese. And I can see that there will be 40 burgers worth of pickles that are all left over. So again, all of those excesses, could we turn them into something? Absolutely. Would it be the same thing that we were making in the first place? No. So how do we apply this information? Well, if I'm given a limiting reactant example, so what I mean by that is, let's say that I am given a practice problem, and that practice problem requires us to determine which reactant runs out first to determine how much product is made. Then what we can do is very similar to what we did in the Wendy's example. We take the reactant, convert it into product, and we do that for every single reactant. The reactant that makes the least product, that's our limiting reactant. That's also how much product is made by the reaction itself. And so that gets us to something that we're going to refer to in a little bit here as the theoretical yield. So more on that in a little bit. So let's take a look at a chemical example problem here. So here we're told that we have acetylene and oxygen, and we have 52 grams of acetylene, 188 grams of oxygen. What we want to know is what is the limiting reactant in the reaction between acetylene and oxygen. So before we can do anything else, first thing that we have to do is establish the balanced chemical equation between the two. And recognizing that this is a combustion reaction, we have a hydrocarbon reacting with a oxygen. We know that carbon dioxide and water will be our products. And so now, just as a matter of balancing, I'm going to need 2 of these and 4 of these. And so 4 times 2 is 8, 2 times 1 is 2, 8 plus 2 is 10, so I need 5 oxygens. So there's my balanced equation.
Chapter 7, we pretty much spoke of already. When we did empirical formulas back in chapter 2.
So we've got our balanced chemical equation now. Now it's a matter of what we do with it. And so again, like the Wendy's example, what we're going to do is we're going to take our 52 grams of acetylene and we're going to turn it into grams of one of the products. Doesn't say which, we're just going to go with carbon dioxide. And we're also going to take the 188 grams of oxygen and turn it into grams of carbon dioxide as well. Now, 2 things are important here. First of all, we want to make sure that we have the correct masses and the correct substances. The other thing that is important in a limiting reactant problem is we want to make sure that we are converting to the same substance and the same unit. If we don't do that, we are going to have major problems with our analysis. So make sure that we are converting to the same thing before we do all the calculations. If we end up getting different things here, we can't make an honest comparison of them. They're going to come out wrong. So start with the acetylene, 12.01 for carbon times 2 plus 2 times 1.01 for hydrogen is 26.04 grams of acetylene in the 1 mole. And then we're going to go from moles of acetylene to moles of carbon dioxide. The ratio there is 4 to 2. And then finally, from moles of carbon dioxide to grams. Carbon is 12.01. Each oxygen is 16. There are 2 of them. 44.01 grams in a mole. Do all of my canceling outs. I get 52 times 4 times 44.01 divided by 26.04 divided by 2, the 3 significant figures, 176 grams of carbon dioxide. Now, we have no idea if that is big or small, at least not until we actually do the conversion and see what the oxygen does. For oxygen, 32 grams in 1 mole. 5 moles of oxygen for every 4 moles of carbon dioxide. And 1 mole of carbon dioxide is the same, 44.01 grams. So you can see the last step in both of these conversions is exactly the same, because again, we're going to the same product, and that's important. It should be the same. So grams cancel, moles of carbon dioxide cancel, I'm left with just grams of carbon dioxide, 188 times 4 times 44.01, divide by 32, divide by 5. 3 significant figures, we get 207 grams of carbon dioxide. So important things to know here. Based on this result, we are getting less carbon dioxide with the acetylene than with the oxygen. So that means that our acetylene is the limiting reactant. It also means that the oxygen is our excess reactant. And then finally, it also means that our theoretical yield for the reaction is 176 grams. Because again, whatever the limiting reactant yields, that's what we should expect as far as our product is concerned. Now, there is one other thing that we could be asked to do. This might show up on one of your homework problems, might even show up on an exam. So be aware. What do you know about the oxygen that's left over? So what if you wanted to try to figure out how much oxygen was left over after the reaction was done? So there are a couple of ways that you could do this. The easiest way is take these two products and subtract them from each other. So we can find out how much excess oxygen there is by doing this. If we subtract the masses of the two products, what that would give us is an amount of excess carbon dioxide. Now, all that we have to do from there is basically just work backwards. So take this bottom equation, this bottom reaction calculation, and run it back the other way in the opposite direction. To get our mass of excess oxygen. So if I did that, 31 times 5 times 32 divided by 44.01 divided by 4, two significant figures this time, we would get 28 grams of oxygen. So 28 grams of oxygen were left over. That means that 160 grams reacted. And so again, that's not going to come up in every limiting reactant problem, but for the ones that do come up, this will tell you how to do it. And so this is where we're going to stop this particular look. And so the next lecture that you see, we will talk about reaction yields and looking at theoretical yield and actual yield and percent yield, and then doing some very simple calculations off of that. So until then, have a good day. So theoretical yield can be determined as just the maximum amount of product that you can make. Actual yield, on the other hand, is just if you do the experiment itself, how much did you make? And so the difference between them is this one has its roots in stoichiometry, and this one has its roots in experimentation. That is the difference between the two. The percent yield is simply the ratio of those two to each relative to each other. Actual yield, the experiment, divided by the stoichiometric yield times 100%. And as we mentioned previously, this yield comes to us theoretically just from stoichiometry. It's the stoichiometric yield kind of out there on its own. And so if I put the two together, I should get a number here that is less than 100%, because ordinarily in an experiment, there are other things that happen along the way, and we end up with a lesser value than what we should.